So let's get started. We are here. We're just starting on topic 7, talking about filter types and filter structures. There's no class on Monday because of election day, so I'll finish this next Wednesday, which is just, again, some more, talking about some other varieties of filter, and then talking about the problem of how to actually implement these in terms of the layout of delays and gains, which correspond to different equivalent algorithms but have sort of some implications. And then we get on to the filter design material. There's a homework assigned today which basically covers the stuff that we actually covered on Monday, but will be due next Wednesday. Okay, so there's a little bit, the phasing between the lectures and the homeworks gets a bit funny at this point, but hopefully it'll all work out and it'll all make sense. Somebody asked me if it was okay to have a team of 3 for a final project. That's okay. I get nervous if the teams get too large, just because I want to, I can't really distinguish between the contributions of all the team members, and I want to make sure that everybody is contributing equally. So if you do want to do that, if you can give me some indication of how the work broke down, one way of doing that is to, have a project where different people can work on different aspects. And that can be quite nice, but, you can put it together to make a whole, which is more meaningful than if you just did 3 individual projects. But again, talk to me about that, send me an email or whatever, and I'm sure we can work it out, if that's what you want to do. Any other questions before we get started? Okay. So, I want to talk about, again, we're still getting into the idea of using what we know about frequency responses, system transfer functions, and the Z-transform to understand how we can build these filters, these useful systems that do particular tasks. And so we'll just look at a couple of variations there. And then we'll talk about, in particular, we'll get back to the idea of phase and talk about this idea of minimum phase filters and their complement, the things that are not minimum phase filters, including maximum phase filters. And then probably next time we'll get onto this material on structures for implementing filters, which is a bit separate. So the two new kinds of filter I want to introduce here are comb filters and all-pass filters. Comb filters basically end up, rather than having a single frequency response, you repeat that frequency response multiple times over your frequency range. And you end up with this filter that typically has a high part and a low part, and they alternate, making it look like a comb. And then all-pass filters are interesting because they're filters where the gain response, the magnitude response, is flat, but the phase response is not flat. And so they are filters that only affect the phase, which is different. Mostly we've been only worrying about the magnitude, so these are kind of the other side of that, but they have a couple of interesting applications and some interesting effects. Okay, so first, comb filters. And basically, there are many ways you could try and design a filter that had multiple stop bands and pass bands, right? You could just try and explicitly place your poles and zeros to get an alternation between high and low gain. But there's this one trick which does the same thing with certain constraints, which is to replace your one-step delays, your z to the minus 1s, with L-step delays, z to the minus Ls. And so this structure, which should look familiar as a simple second-order filter. Up till here, we've got a basic moving average filter with some different gains here, so a delay line set of gains summing up. And here we've got a feedback, a second-order denominator to our Z-transform, giving us a couple of poles, again, where these gains will define what the actual poles are, these gains being the coefficients of the denominator polynomial. So if these were just regular single-step delays, this would be a normal 2-pole 2-0 filter, which turns out to be a very important basic structure. But instead, there's z to the L delays, z to the minus L delays, which means that an impulse goes in here, it sort of works its way through here, and then only L steps later does it appear at the output. And so you can sort of see that what happens here is it's sort of doing the same thing. If you had a one-step delay here, you put an impulse in, then you get some sequence of values coming out here. And now it's going to basically be the same sequence of values, but they're going to be stretched out by a factor of L, because everything happens L times more slowly, right? It takes L times longer for the impulses or whatever signals to get through these delay lines. So it behaves at a longer time scale, and because of the reciprocal relationship between time and frequency, making it L times as long in time makes it L times as compact in frequency. The frequencies are L times lower. That's just the intuition. We'll see exactly how it plays out in a second. So, in particular, if we had this system with those, with certain gains, but with one-step delays, we could call that like our parent system H of n. And then we have our new system G of n, which is that same set of gains, but with the delays replaced by L-step delays. And so, if you actually think about what happens here, if this starts off initially at all the delays are at zero state, right? So the outputs, everything is zero. If you think about the impulse response, you put an impulse in here, you get some non-zero value coming out here, assuming this value is non-zero, but everything else here is zero. Then at the next time step, the impulse is hidden in here. It's in like the first delay element in this chain of L delay elements. And so everything is zero, so the output is going to be zero. So everything stays zero until the impulse appears here. Oh, wait, hang on. It's also the first output is plugging down through here, but this still is also invisible. Then L steps later, the impulse comes out here, and the first output comes out here. They feed in, we get a new output, goes back in here, but then for the next L minus 1 steps, everything disappears into this delay line and then comes out and loops around. But what's going to happen is that for all the L minus 1 steps in between each of our non-zero outputs, we're going to get zeros, right? That's just because there's no way for something to happen like 2 steps later. There's no way for a system initially at zero with just an impulse as input to get something to happen at that point, provided all the delays are L steps. So it's literally just the original impulse response upsampled by a factor of L, upsampled by inserting L minus 1 zeros between every point. You see that? You can sort of step through it if you like. At some, think about what the machine does, what the inputs and the outputs of the delay elements are at every time. But you see, that's what works out. So now we know what the impulse response of our factor of L interpolated system is going to be, if we know what the impulse response of the order 1 system is. And so we can work through from that. Yeah?
Does it necessarily need to be only zeros? I mean, can we represent some other element just to get delay? Or
just to get, just to get what?
The delay, Z bar minus F. Is it like necessarily needed to be zeros? Or
yeah.
Can it be something else?
Yeah. So the question is like, well, we've got this delay in here. Why are we outputting zeros there, right? Why you could imagine, if you were trying to plot this extended impulse response, you could imagine, say, well, let's make it a linear interpolation or something like that between these points. You could join them up with something more sensible. You could certainly do that. And if you wanted to do the thing that I kind of mentioned at the beginning, which is like, I want to take the same frequency response but squeeze it down, then that's kind of what you'd want, right? That sort of squeezing it down would be like taking the original system, the analog system, and sampling its impulse response more finely so you get a more kind of, a stretched out version of the impulse response. That would give you something different. Here, and you wouldn't be able to implement it like this, right? You'd have to implement it with a lot more, with an output after every delay element, which was the particular value of the impulse response you were trying to implement there. So instead of having just 5 coefficients, we'd have 5 times L coefficients, something like that, right? This is one thing we can do to generate a system which has something like that behavior, but it certainly, this is the one that will have zeros in between, right? Because as I said, as I've sort of tried to explain, once the impulse and the first output disappear into these delay elements, there's nothing to generate any output, so the output has to be 0. If you fed in a more complex input that wasn't just an impulse, then obviously the output wouldn't be 0 at all those in-between times. But if you feed in just a single impulse, then you just get these outputs every L samples and zeros in between. And of course, the impulse response is the thing that we care a lot about, because if we can analyze the impulse response, then we know we can quickly predict what the output is going to be for any arbitrary input just by multiplying them in the frequency domain. Okay? All right. So now we've got this impulse response with all these zeros in it. So now we can calculate the Z transform or the frequency response Fourier transform using our standard equation. That's just the sum of g of n z to the minus n. But because g of n is h of n divided by L, where n divided by L is an integer and 0 elsewhere, then we can replace n with n divided by L, as it were. So then we get these individual points coming out, and then the exponent here is e to the minus nl. Hopefully, I didn't explain the change of variable very clearly there. But so what I haven't written down here is the identity, right? Which is that what this picture is showing is that g of n is equal to h of n divided by L, where n divided by L is an integer, and 0 otherwise, right? So basically, when n is a multiple of L, we get the corresponding value of h coming out, and otherwise you get zeros. That's just what this plot has shown. So then if we expand the summation given that, then we only have to care about the values of n, where n divided by L is an integer, and so I've rewritten n as that thing, n divided by L. And of course, in those points, the z to the minus n points is just going to be z to the minus something times L. What this amounts to, if we look at this, the reason I read it like this is because if we look at this, this is exactly like the z transform of h, except instead of z to the minus n, we've got z to the minus nl. So it's h of z to the L, right? If we took the z transform, which would just be the sum of this h of n times z to the minus n, and replace the z with z to the L, then it would be z to the L to minus n, which is z to the minus nl, and we get this. So this means if we have our parent h of n, which is with the one-step delays, and we build a g of n by replacing the one-step delays by L-step delays, then the z transform of that system is just h of z to the L. So it's the same polynomial, but with the z's replaced by z to the L, which of course kind of makes sense here, because here we replace the z to the minus 1s with z to the minus L. So yeah, it works even in that domain. But here we've shown that it works, by applying the z transform equation. So then the question is, well, what does that mean? It means that if I had h of z, I had the h of z, my original filter, over the entire z-plane, I want to know the value of g of z, the system function over z for my new system. I just take that value of z, I raise it to the power L, and I read off on the h-plane, on the h system, what it's going to be, and I get the function out, which is a little bit strange, but here's what happens. In particular, if I use z equal e to j omega, the unit circle, which of course is the points on the z-plane that give me the Fourier transform, then I get that g of e to the j omega is h of e to the j omega to the L, h of z to the L for z equal e to the j omega, which means that it's the value of the Fourier transform frequency omega for my derived system is the value of the Fourier transform of the original system for omega L, L times the frequency, which means that I'm sort of looking further out in frequency. And so if my h of e to the j omega is some kind of low-pass filter here, so this is minus pi to pi, this is a filter that has a bump around 0, a 0 at omega equals pi, and sort of something in between, then this 0, which occurs in h of e to the j omega for omega equals pi, is going to occur in g of e to the j omega for omega equals pi on L, right? Because that's the thing that's going to give me omega L equal to pi. And so here it is. This is for, this is actually for, let me get this right. So this is for L equals 6, right?
Because you plug this L in, and then it should have the lower thing at the same place, right? The 0.
Should it be 1 over 6? Should L be 1 over 6? Well, on the previous slide?
No, on this slide.
On this slide. So here I'm looking for the argument to h of e to the j omega, which gives me pi in here, right? So, I mean, I, as you can tell, I'm tying myself up in knots, but I think this is correct, which is that if omega equals pi on 6, so I'm looking for the value of g of e to the j omega at this point here, then I multiply it by L, let's say 6, so then I evaluate h of e to the j pi on 6 times 6, h of e to the j pi, which is this point here, and that gives me this frequency here. And so the idea here is that if this is the z-plane for h of z, the parent filter, and in particular I'm trying to show the values of a complex value by using both saturation and color here. And so the values close to 0 are white, the values with very large magnitude are black, and the values with magnitude around 1 are colored, and then their phase is indicated by the color. Then this is the same slightly weird mapping of complex values to colors for z to the L. And what happens is, well, if z was 0, then z to the L is still 0. If z was some very large value, then z to the L becomes an even larger value. So it's getting darker as we go out, so it gets very dark. It gets dark more rapidly because we're raising it to the Lth power. If the magnitude of z is 1, so we have a saturated color like this, then z to the L still has a magnitude of 1, so we still have the saturated colors around this unit circle. But if the phase of z is, pi on 2, then when we raise it to an Lth power, it's pi on 2 times L, and so it's we've gone through the entire cycle, the green to orange to blue. We've done that already by the time we've got a quarter of the way around the circle here. This is clearly four cycles, so this is actually L equal 4 here. But this is kind of like you can, for every, if this was h of z, then this would be g of z, and then to find the values for the z transform g of z, we'd sort of find the point, we'd look at a point here, look at its color, and find the point on this curve that had the same color, the same hue and saturation. And then that would tell us the value of z such that z to the L was this value. And then if we get h of z for this point, then we get g of z, which would be h of z to the L for this point. So that this picture, I don't know, you see what I'm trying to do, which is to explain the mapping between the two planes. If I have a mapping z goes to z to the L, then it takes the complex plane, maps it onto the complex plane, but it stretches it so that the points close to 0 tend to stay close to 0. The points beyond 1 tend to get, it gets larger faster. But the points on the unit circle remain on the unit circle, but they get sort of wrapped around multiple times. And it's this repetition of colors, the fact that e to the j theta to the power L is e to the j theta L, which is an angle, but the angle is ambiguous with 2 pi. So we get these repetitions of these values for e to the j theta L. Of course, these points out here are simply the values of h of z on the semicircle. And so these values here, which are the values of g of z on the semicircle, correspond to the values of h of z going round this circle L on 2 times, right, for the semicircle. I basically said the same thing about 3 different ways. The first way is, well, the result is that g of e to j omega corresponds to L repetitions of h of e to j omega squeezed in, right? So between minus pi and pi, we have 1 repetition here. When we do it here, we get L repetitions, which means that we have these features repeating and compressed in, which is the same as saying that, you know, this mapping maps the entire z-plane to the z-plane, but with repetition, so it's a one-to-many mapping here, because there are several values of z such that z to the L is the same point, right? If I have z equal to 1 or z equal to j, then z to the 4th power is still 1, right? Because j to the 4th, or minus 1 to the 4th, or minus j to the 4th, they all give me 1. So this is a one-to-many mapping here.
I have a quick question.
Yeah.
Shouldn't it still be 0 at pi though, even if you do it L times? Just like this original signal.
That's a nice point. So here, this thing had a 0 at pi, but here, this thing's now got a 1, a maximum gain at pi. Let me try and work it through. So we're saying here, this point is red, right, which is where the 0 is. And here, this is actually L equal 4 and L equal 6. But we see it goes to red, to red, to blue. So this is sort of looking like, no, we come back to 0 at this point. Now, what's funny is the way we've drawn this, right? We've drawn this sort of half a cycle positive, half cycle negative. It would be more obvious if we drew it out as one complete cycle from 0 to 2 pi, right, which would just be the periodic extension of this. And then, if we compress it in by a factor of 2, it's clear that the 2 pi, which was a maxima again, comes in at pi. If we compress it in by a factor of 3, then it would be the 3 pi, which would actually be a 0 again that comes back to make the 0. So it depends whether the power that we're raising it to is odd or even. If it's even, then we're going to get a maximum coming in at pi. If it's odd, then we're going to get a minimum, because basically this has a minimum at every odd multiple of pi and a maximum at every even multiple of pi. This thing here is going to be L times pi, and so the value of L times pi depends whether L is odd or even, right? It's, the values at 0 are the more better behaved ones, so they will always occur at 2 pi on L, right? Which is 2 pi on L is 2 pi on 6, or pi on 3 here, 4 pi on L, 6 pi on L, etc. So here, with a maximum at 0, we get these maxima occurring regularly spaced. If we had it the other way around, so it was like if we had some, bandpass filter that had a couple of maxima in here, then we would get these things occurring around every one of these spikes. So they would sort of be maybe unevenly spaced, but they would be then repeating every 2 pi on L radians. Yeah? What? Sorry, what?
I'm looking at what mathematically you can determine you get a maximum.
Yeah, so that, right, why is it a maximum or minimum? The point being, this is just some arbitrary parent filter. This is h of e to j omega in this case, and it could be any filter we want. We started off with the structure here, which was a simple 2-pole 2-0 filter. So maybe that's a filter that has some zeros here. I don't know, that's actually only 1 0, and a pole around here or something like that. But it could be any filter. We could have made it a simple, 2-0 filter, or we could have made it like a 12th order filter with a lot of poles, a lot of zeros. You can have a very complex shape in here. But whatever that shape is, it just gets squeezed in and repeated multiple times to give us our comb filter. And so just by the single operation of replacing the delays with L-step delays, the generic thing we do is take the frequency response and repeat it L times in the 2 pi cycle. Why is that even interesting? Well, it turns out that this pattern, where we want to do the same thing every regularly spaced frequencies, is something that makes sense because it turns out that signals that are periodic will have Fourier transforms, which are approximations to Fourier series, approximations to a sum of discrete sinusoids which are all at multiples of the fundamental frequency. Omega 0, 2 omega 0, 3 omega 0. And so we can build a filter which, for instance, selectively passes those frequencies. Or if we had the filter that was a high pass like this, it would then selectively cut those frequencies. And for instance, that's how I mentioned last time I built this filter to remove 60 hertz hum. And that's exactly how you do it, just by having a system with a delay that's exactly the period of the 60 hertz cycle, and then having a high-pass filter that removes all of those harmonics. So, I mean, this is quite esoteric, right? There's one occasion when I've used one of these, but it's not something you use very regularly. But the reason to focus on it is just because it gets us thinking about the way that the filter response is a function of, it's derived from the z-plane representation. And so we can actually do modifications directly on the z-plane. And we can then, if they are interesting, if they're helpful, then they give us a filter directly. And so, or at least, if we in this case, we can have a modification which is, in terms of modifying the delays, but we can understand it very simply in terms of the z-plane, and then we can see how that gives us this result here. And that's something that we'll look at again when we're talking about transformations between filters. Okay. So the other kind of filter I want to talk about is this all-pass. Any more questions on comb filters? Okay. So I want to talk about all-pass filters. And as I said, an all-pass filter is called all-pass because it lets all frequencies through. And indeed, technically, it lets them all through with the same gain. So there's no differential amplification or modification of the amplitude of any frequencies as a function of frequency. So the magnitude squared of the frequency response, the magnitude response, is some constant value. And of course, that means that if we just apply a gain of, in this case, 1 over square root of k, the amplitudes are unchanged. It's got unity gain for all omega. Now, of course, we know a filter does this if you convolve with a delta, which is the identity operation in convolution. Then you get the same signal out, and so it meets this. But that's obviously not very interesting. That's a degenerate or trivial case. So to make the interesting ones of these, we have this property, but we also have it that the phase response is not a simple linear phase or zero phase response. The phase response has some nonlinear dependence on frequency, and so it's done something interesting. It's done something with the signal. So here's an example. Here's the gain in dB from 0 to minus 20, and it's just 0 dB for all frequencies. But here's the phase response, the angle, in this case in degrees, as a function of frequency. And it's got this response, which looks kind of like what we saw with a pole, where it sort of has, changes rapidly and then it flattens out. And so we've got a phase response without a magnitude response. Why do we want to do this? Well, if we have a signal that's been distorted somehow, gone through some kind of system, we could look at its magnitude response, measure the gain that a sinusoid experiences at different frequencies, and then we could design a filter that compensates for that gain response. But it might be that after we've done that, we've flattened out the gain of every frequency, but we still don't have a flat phase response, which would give us problems if we try, would give us basically group delay distortion, that the group delay would not be constant, and so you'd have a distortion of the signal. So we can then, after we fix the amplitude, we can then go and use these kinds of filters, these all-pass filters, to fix the phase. Now, of course, we could do that all at once. We could design a filter which tried to fix the amplitude and the phase in a single operation, but that would be a harder job, right? We'd have to have design tools which allowed us to control both the magnitude and the phase. We have design tools that allow us to control the magnitude, or we'll see them, and so sometimes we then want to separately control the phase, and so that's why these kinds of filters would be the thing we would use. There are other reasons why these can be interesting. We'll see that the actual modifying the phase response without modifying the amplitude response has an interesting effect on a signal. And moreover, there's this nice theory of building filters by combining all-pass filters. That if I have two filters with flat magnitude response with different phases, then if I add them together, for instance, then the resulting filter no longer has a flat magnitude response because it's about the phase interactions between the outputs. And so you can have these kind of families of filters where you have a couple of all-pass filters, and then by adding them you get a band-pass filter, and by subtracting them you get a band-stop filter, because you're sort of either cancelling or reinforcing particular frequencies. And so they have a variety of interesting practical applications in terms of these multiple behavior filters. But right now, it's not obvious that we can actually build a filter like this. It's like, well, we know how to get a phase response like this with a pole, but we'd get a magnitude response as well. So how are we going to build these filters at all? So here's the answer. An all-pass filter can be constructed like this. We're going to design it as it's a z polynomial, its transfer function. The z polynomial has a numerator and a denominator, and they are both, in this case, order m polynomials in z, but they have coefficients which are the reverse of each other. So this one is d of m plus d of m to the minus 1, z to the minus 1, plus d of m minus 2, z to the minus 2, down to d of 1, z to the minus m minus 1, and then 1 times z to the minus m. The denominator is 1 times z to the 0 plus d1 times z to the minus 1 plus dm minus 1 z to the m minus 1 and dm z to the minus m. So we call these mirror image polynomials because if we write them down as just the coefficients, then the vector of coefficients are the same, but they've just been flipped. Right? In MATLAB's way of representing it, it would just be a flip of that vector, but they'd be the same coefficients. If we multiply through by z to the minus m, then actually they become the same. And then if we replaced z with z to the minus 1 in here, so replace z to the minus 1 with z, and then divide through by z to the m, we'd get this. So we can express them in terms of a single polynomial dm of z, which, say, could be the denominator polynomial. And then we can say, well, the numerator polynomial is just dm of z to the minus 1 times z to the minus m. That'll, by reciprocating the z, then we end up reversing the order that the powers appear in. So we get this mirror image polynomial. But this is just to make sure the powers are in the same range of z's here. So now we've got the polynomial for the poles, the polynomial for the zeros, and they're the same polynomial but with a different argument here. So we know that this overall system is going to have poles where this polynomial is 0, right? So the roots of this polynomial, the value of z for which dm is 0 are going to be the poles. But the values of z for which dm is 0 are going to be the values of z to the minus 1 for which this thing, the numerator, is 0. So the zeros of this overall system are going to occur at 1 over the values at where the poles occur. So if we have a set of poles lambda, then we're going to have a set of zeros zeta, which is simply 1 over lambda. Right? Lambda I with braces and lambda zeta I with braces is 1 over lambda I for each of the existing poles. So that's a very specific structure. So here's our form of our mirror. I haven't proven that this is an all-pass filter yet. I'm just saying it is, but Let's just examine what this particular structure means. So as long as we've got a set of poles here which are stable, meaning the poles are inside the unit circle, then we can flip that polynomial around and get our set of zeros for our numerator, and the zeros are going to be 1 over these places. Now remember, we looked at this before when we were talking about the reciprocal zeros in the FIR filters, the symmetric FIR filters, that if I have this is my lambda, then if zeta is 1 over lambda, well, its radius is going to be 1 over r, so it'll be, given that the radius of lambda is going to be inside the unit circle, the radius of 1 over lambda will be outside the unit circle. But its phase, 1 over e to the j theta is e to the minus j theta, so it's going to be negative down here. So actually the reciprocal of this 0 here is this, the reciprocal of this pole here is this 0 here. The reciprocal of this pole here is this 0 here. But because the poles always occur in conjugate pairs for a real valued impulse response, the zeros will similarly occur in conjugate pairs. And so what we end up with is this neighboring 0 just outside the unit circle in both cases. And here is a pole on the real axis, which is a little further inside the unit circle. The corresponding 0 is therefore also on the real axis, but a little bit further outside the unit circle. If this is, a half, then this is at 1 over a half, which is 2. If this is at 0.9, then this is at 1 over 0.9 or 1.11, something like that. And so this pattern of poles inside the unit circle and zeros at the same angles but at reciprocal radii outside the unit circle is the characteristic pattern of an all-pass filter. You could imagine it with poles outside the unit circles and zeros inside the unit circle, but those would be unstable filters, that if we ran them causally, they would diverge, and so they wouldn't be useful to us. They wouldn't have, in their causal form, they wouldn't have convergent Fourier transforms. So these are the only ones that we actually deal with. Just from our understanding, so this is a z-plane representation, and in theory we can use our existing tools, our existing insights into how to handle these things to predict what its magnitude and phase response is going to be. The magnitude response, it's going to be the ratio of the vector from all the poles to the point of the unit circle and all the zeros to the point of the unit circle. These vectors from the pole and the 0, we can see that they're going to be sort of the same length, right? Because particularly in this case, they're sort of the same distance from the unit circle, and they're sort of in the same place. So it's not impossible to believe that the ratio of these two is going to cancel out, and the ratio of these two is going to cancel out. And it turns out that that's exactly what happens, which is why this is an all-pass filter. But the phase responses are not going to cancel out, because the phase responses are obviously going to be very different, and plus, one's being added and one's being subtracted. And so that's why we have a phase response that has this, this kink in it, which looks very much like the kink we get from the pole alone, but in fact it's been enhanced by a phase response contributed by the 0. And we get this non-linear phase response. The group delay, remember, is the local slope group delay, which is the effective phase shift of an amplitude modulation of a carrier at that frequency. Sorry, the effective delay of a amplitude modulation on a carrier is the local slope. So here we have a large group delay for frequencies around here, but for other frequencies, the group delay is smaller. So the amplitude modulation of frequencies in this range, if there is one, will be effectively delayed more than these other frequencies. The phase is always decreasing, right? So the phase function is the phase function is the angle between each of the poles to the point of the unit circle, the negative of those, plus the angle from each of the zeros to any point in the unit circle. it's difficult to figure out exactly what's going to be in detail, but if you think about the angle here from this pole, it starts off negative, goes up, keeps increasing all the way around until here we've sort of gone an entire revolution around this pole, and so the total phase, if it weren't for the 2 pi rep, would be 2 pi larger. Whatever it is here, it's the same angle, but it's gone a way around, so it's gone all the way down to 2 pi. And in the case of a pole, it's the negative of the phase, so the phase would be 2 pi lower due to this one pole. The 0, the phase sort of starts off negative, gets positive, gets negative again, and then starts going up again and goes positive. Because the 0 is outside the unit circle, we don't loop around it, and so the phase wiggles up and down, but it goes back to 0. It goes back to the same value at the end. Right? There's a difference between looping around a pole, in which case you get a phase which accumulates, and so doing a loop near a 0 where the phase wiggles around but ends up the same. And so once you've done the entire loop, you're always 2 pi times the number of poles further down than where you started, except that it'll wrap around. But the curve always looks something like this, so you accumulate extra phase. I wish I could have explained that better. But there is this interesting, again, if you look at those pictures of the phase due to the different routes that we drew when we sort of worked it out geometrically, there's a big difference to what happens at the end, whether you're inside or outside the unit circle, which is whether the contour that you go about encloses or does not enclose the route that you're evaluating. Okay, let's quickly look at one of these all-pass filters. Hi, yeah.
So doesn't each pole contribute a specific amount of phase shift in the system? And in the fact that if you have like 3 of them, it's going to be the same amount of phase shift, but it's going to be sort of 3 times.
Doesn't each pole contribute the same amount of phase shift? Once you've gone all the way to 2 pi, then they each contribute 2 pi of extra phase shift. So this thing down here, this is actually, I'm only going from 0 to pi, but because of the symmetry, it ends up giving me 3 pi of phase shift here, and it would give me 6 pi. This thing would be symmetric around here and go down to 6 pi at the end. But at any particular frequency, the actual phase contributed by each of these poles varies depending on frequency. So it's not just 3 times the phase of one of them because they're in different places, right? Clearly this one's got a very different phase characteristic to this one. So at any individual frequency, they have different contributions. But when you get the whole thing around, then they all give a total of 2 pi. So what I wanted to just show you one of these in MATLAB to show you what's going on. So actually, if you go to the MATLAB scripts here, and there's a little diary here. So all we're going to do is we're going to define a couple of routes, a couple of poles here, so radius 0.9 and angle 0.1 pi. If you take the actual routes and then you can use the poly function with a couple of routes. Here I'm taking the root and its conjugate because the transpose operator also conjugates. So I generate a polynomial from those, and that'll give me this polynomial, which is the second order polynomial, to give me those particular roots. And then I could generate a numerator polynomial simply by flipping this. Flip LR just takes the vector and reverses it. And so then I can get the actual filter response here. So, okay. So this is the pole 0 plot. So here's my poles, which are at radius 0.9, angle 0.1 pi. And then I generated the polynomial for the zeros simply by reversing the polynomial. But lo and behold, the zeros occur at these reciprocal locations, just as we showed that they would. So then we can look at the frequency response of this. So frec z gives us the frequency response of a filter defined by its numerator and denominator coefficients. And here it is. The magnitude in dB, this is like 0 by 10 to the minus 14. So it's like basically 0, has a little bit of numerical noise here, but it's basically 0 for all frequencies. But the phase response is this phase response that we saw, that around 0.1 pi, which is where the poles and zeros are, we have this large rapid change in phase based on the idea that, the phase response changes most rapidly when the values on the unit circle which are closest to the roots. And then it's more gentle phase response for other frequencies. The group delay, which is the local slope of this function, we can also, MATLAB has a group delay function to evaluate that. And here it is. This is just the negative of the derivative of that phase function, has this peak at 0.1 pi, and it drops off elsewhere. Interesting, the group delay is, the units are in samples. So this is saying, yeah, if you have a 0.1 pi radians per sample sinusoid, you feed it into a system with some amplitude modulation, then the amplitude modulation envelope will experience getting on for 20 samples of delay. You can read it directly in that way. So that's, our filter, and we can actually plot the impulse response, I guess, of that filter BA1 and then zeros, say 100. Right, so I'm just using the filter to, I'm trying to move this up without much success. Okay, here we go. I'm using filter to implement this filter and then just feeding in an impulse followed by 100 zeros as the input. And then if we just plot H, or stem H, this is the impulse response, and it's, I don't know, this looks like a typical pole response, which is coming from those two poles in the denominator, but there's something else going on at the front that's got this large initial impulse. And so that's all it is, right? It's the B part, right, which is just an FIR filter whose impulse response is 0.81 minus 1.17, 1.0, right? The reverse of the denominator coefficients. It's that FIR filter feeding in a couple of poles that have this nice kind of decaying pole response. But the net response is this flat magnitude response. Yeah?
Can you just explain once again what exactly is this? Is that the inverse of the...
Yeah. So I generated this root here. I then generated A as the polynomial of that, which is just this. And so here, this filter, which is, this is the denominator polynomial, the denominator of the Z transform of some roots, some poles, is this. So it's like, which means that it's if you feed back with a delay of plus 1.7 from one step delay and minus 0.81 from two steps delay, then when you work out the characteristic equation, it becomes to this. And when you take the roots of that, you get these, right? So this thing alone, frec Z of 1A, gives me this nice pole response here, right? This is the frequency response and the phase function. Is that right? BA. That looks like a nice pole response. I'm not sure why the phase function isn't, because it's only between 0 and pi. Right? And then, but then I take B as the flip LR of A. So it's the same values, but now in different order. And if I look at the frec Z of B, so taking these just as zeros, then I get this thing which is now looks, it's where the other one had a peak, this one has a minima, right? But the phase function is still kind of this decreasing thing. And then if I put them together, which is really the same as just taking two systems and applying them in series and multiplying them together, then I get this thing with the magnitude response is flat, but the phase response is this non-flat thing. I sort of wave my hands there about what's happening with the phase response. There's a linear phase term which gets added to those phase responses, so it's not quite the story that I had before. But the essence is the same. That both of them have non-complementary phases. So when I subtract the phase response, or when I add the phase response to the two systems together, I get this more complicated, extended phase response. Okay, so what does this thing mean? Well, this is a filter that doesn't modify the magnitudes of any Fourier components, but does modify their phase, that is, shifts them in time. So if we take a complex, a real signal, not a complex signal, but a complicated signal like a piece of speech, right? I hope this works.
Football team coach has a watch, then has a dime.
Okay. I can take this signal and put it through this filter. And actually, if I listen to it, it doesn't sound that different.
The football team coach has a watch, then has a dime.
If I look at its, but if I look at its frequency, the point is that the filter hasn't changed the magnitude, so I can actually do this many times. I can put a loop here, put this signal back through the filter over and over again 100 times. And now if I look at the Fourier transform of the original signal and the filtered signal, if I just look at the Fourier transform magnitude, and so this plot spec just does FFT and then cuts off the second half and labels it so that you can see the frequencies. Here are the spectra of the original signal, the speech here, and the signal after I put it through the filter 100 times, Y. But this is just the magnitude, and the magnitudes are all the same, right? But the phases are not the same. Well, if we listen to the signal now,
The football team coach has a watch, then has a dime.
something pretty weird has happened to it. And one way we can look at that is by using the spectrogram. Now, we haven't really spoken about the spectrogram yet, but the spectrogram basically applies the Fourier transform locally in time. So you can get a picture of the the frequency content at a particular point in time. If we look at that, this is the spectrogram of the original speech, which is here's the time axis, here's the frequency axis. So it's saying around 0.5 seconds, we had a bunch of energy down here, some energy up here, and less energy elsewhere. Here's what happens after we put it through this filter with this group delay. Now, each row of the spectrogram is like a single frequency or a very narrow band of frequencies, and the color is showing you the amplitude of that band of frequencies. And so this is group delay we're seeing here, that for these frequencies around 0.1 pi, that is 0.2 of the Nyquist rate, no, 0.1 of the Nyquist rate, so 800 hertz. 0.1, yeah, 800 hertz here. They've been delayed by 20 times 100 samples, so 2,000 samples, which is a quarter of a second, an eighth of a second at 16 kilohertz. And so that's what we're seeing here. All these frequencies have been delayed. And so actually this shape here, we had these nice vertical structures here corresponding from the beginnings of a sound, right? There's no energy in this gap between the words, and then there's this onset of energy here. And now this onset has been shaped, and the shape is actually exactly the group delay function we saw, that it starts off, has a peak, and then it decays away. And so that's what we're getting here. When we hear that, what we hear is these kind of like these shaped onsets as these kind of rising squeaks, these rising tones. We listen to it again.
The football team coach has a watch, then has a dime.
They're kind of like these bubbly squeaks, but that's actually just the effect of like these rising sinusoids and rising and falling sinusoids that come from those structures there. So here we see that, well, phase modification amounts to modifying the time structure of these signals, and a drastic phase change can distort your overall signal, right? That we've filtered the signal, we haven't modified the energy in any frequency band overall at all, but we've moved it around in phase, meaning we've moved it around in time, and so we end up with a signal which is severely distorted compared to the original. It was because the repeated application of the filter didn't modify the amplitudes at all that we're able to do this. And now, I mean, this is effectively a 200th order all-pass filter, because it's a second-order filter applied 100 times. So it's like we put it through 100 of those all-pass filters to give us a 200th order filter. The magnitude response is still flat, but the phase response is very, very severe. Yeah?
So to get an all-pass
Yeah.
amplitude response,
Yeah.
instead of having a frequency response like this, what we just did, making the mirror images of numerator and denominator coefficients. Why can't we have a filter whose impulse response is just a unit impulse? I mean, even that has an all-pass frequency response.
It does, right? So if a filter, so that's interesting, right? We said that the all-pass filter is simply, d of z to the minus 1 divided by d of z with some z to the m, maybe some gain in here. So if d of z, if this thing is like, well, if this thing was, say, 1 and then a bunch of zeros, then this thing would be a bunch of zeros and then 1, which would, this would be kind of a degenerate version of a polynomial because it would look like it was a high-order polynomial, but in fact it's only got one term in it. And this would be the same. And so all we'd have is, at worst, a delay, right? That depending on how many zeros we put in here, we'd have a different amount of delay in our FIR part. But the magnitude response, but it would still conform to an all-pass filter. And so that's true. A pure delay, including, which is, an impulse response that just has a single impulse in it at some point, a pure delay is an all-pass filter. But the phase response is not very interesting. The phase response is, of course, just linear phase, right? So, and if the delay is 0, then it's a linear phase with a slope of 0, so it's 0 phase. It's identity. Even if there's a non-zero delay, we get a phase response without a magnitude response, but the phase response is not very interesting because it's just shifting it in time. So that they are technically all-pass filters, but they don't do so much for us. Whereas the ones that are interesting are the ones that have these nonlinear phase responses. But that's just a question of taste of what you find interesting. Yeah.
So if we design an all-pass filter like that, we could, for example, take a pole at something with magnitude 0.2.
Yeah.
But then your explanation of why all the frequency included that they would be close to the unit circle. So
yes.
Do we try to avoid that they're too far away from the unit circle?
There's nothing. So what would happen if the pole was not close to the unit circle? So if its radius was 0.2 like this, then here's our A polynomial, here's our B polynomial, here's our pole 0 diagram, just to check that it's what we expected. Okay, so here are these two poles at radius 0.2 from the origin, and here are now the reciprocal zeros, which are going to be at radius 5, more or less, right? So they're, because as these ones get close to the unit circle, then the reciprocals also get close to the unit circle. Right on the unit circle, they coincide. As these get close to 0, then 1 over r gets large, and so the zeros get far away. So this is still an all-pass filter. If we look at its frequency, its magnitude and phase response, it's still flat. But now the phase response is less dramatic, right? So if it were just a straight line here, it would be a pure delay. It's not. It's got a little bit of a curve to it, but not much. And in fact, because these things are, because the z-plane poles, the z-plane features are so far from the unit circle, we don't see any kind of local behavior. It's like, well, their influence on these points is fairly gentle, varies quite gently with frequency. So now if we did the same thing of applying this filter over and over again, and then look at its look at the spectrograms, we should see. Well, let's look at the group delay just quickly, just to check what we're looking for. So the group delay here is that at low frequencies it's got a little bit more delay. So that was the initial slope was a little more negative, and at higher frequencies it flattened out a bit. So the delay is 3 samples down to 1.5 samples. So when we apply it 100 times, we expect to see a sort of 150 sample shift, which at 16 kilohertz is 10 milliseconds. So it's more it's pretty small, so that you can't. If we zoom in, The different coloration is just because of the auto scaling that MATLAB applies. But if we zoom in on this impulse here, actually our spectrogram is not showing us terribly good time resolution, but there's a little bit of delay of this energy in the low frequency compared to the high frequency. That's all that's going on. Right. Yeah?
I'm confused about one more thing. So when we looked at the magnitude response, it was all zero. So why doesn't the
Yes.
magnitude make everything zero?
Yes. When I did FREC-Z here, the magnitude response is all zero. It's like, what? So you're multiplying all these by zero. This is magnitude response in decibels. So this is 20 times log base 10 of the magnitude response. So the actual gain is 1, but the log of 1 is 0. So 0 dB is a gain of 1. Yeah?
Any specific reason why we need a non-linear phase responses against a completely linear? I mean, does it make any...
Why do we care about a nonlinear phase response versus a linear one? Well, in general, it's nice to have systems with linear phase responses because that means they haven't changed just the timing relationships between different frequencies, right? A linear phase means that the phase shift is proportional to frequency, but of course the duration of a period is inversely proportional to frequency. So, the time is phase times frequency, phase times period, right? So if my period is 1 millisecond and I do 1/6 of 1 millisecond, and the total delay is 1/6 of a millisecond. So it's like pi on 3 times divided by 2 pi times 1 millisecond. So linear phase just means constant delay. We already showed that a constant delay corresponds to a phase function of minus d times omega linear phase. So in general, if you want to have a signal which is not distorted, you either have a zero phase, which is d of 0, or you have a linear phase, where the signal experiences the same delay at all frequencies. All-pass filters are for the situation where you don't want that. For some reason, you do want to change the relative delay of different frequencies. And that's typically because maybe they've already been messed up by something else, and you need to try and fix it. Right? So you put it through some system that had some poorly behaved phase function, you're trying to fix it up. Or it might be that you've got some other purpose you're trying to... You might be like, for some reason, that you've got a signal where if only you can line up the phase of this component with the phase of this one delayed by a certain amount or shifted by a certain amount, then you'll get something which is functional to you, right?
Does that depend on the band of interest, or probably a few frequency components we are actually specifically interested in?
Right. It depends. It would depend on some specific application, right? I mean, there's no particular reason why. There are many different things we can try and do with filters. Normally, we assume there's some well-structured signal in there that we're trying to get out. So that's the idea of having a bandpass filter with a nice flat phase response. But there could be other situations. So, certain kinds of physical processes will be exhibited in terms of a phase characteristic. So, a resonance system will often be characterized by a particular phase shift at the driving frequency, because suddenly at the driving frequency you have energy being shifted around, so you get this phase shift. And so you might want to try and detect particular phase shifts. And if you had a bunch of different components with different phase shifts you're trying to detect, if you could line them all up, then if they were all going through cosine phase at the same time, then you get a big pulse in the time domain. That might be a useful way to detect them. So that would be like why you'd want to be able to apply arbitrary phase shifts, something like that. But it's very much specific to the scenario you're using. I recognize that I have not given you tremendously good motivations for why you'd want to design phase functions, but believe me, it will occur that you'll at one point you'll want to modify a phase, and so that's when the all-pass function is your friend. Okay. So we've sort of seen that this works, right? We took a system, designed it with its poles, gave it zeros that were the reciprocals of those poles, measured the overall frequency response, and it was flat. Oh, let's just take a look at... we've looked at this system. So which one is this? Let's go back to the original one, where the poles are a little more dramatic. So that was, I have to redefine Z0, and then redefine A, and then redefine B. Now, you remember the function I had to plot, the sort of the rubber sheet version. I've written that into a single function now, so I forgot what it's called, viz. Yeah, here we go, viz zt surf. So, yeah, this is now that. Oh, look at that. Didn't work. Let's try that again. Let's have the actual z's that I wanted, the A and the B. Okay. So this is what it looks like. So that's kind of what we expect. It's got these two poles just inside the unit circle giving us these big spikes in the rubber sheet. Got these two zeros outside the unit circle giving us these two negative going spikes in this log magnitude scaled thing. And here are the poles and zeros plotted. Now, you can sort of see that, well, these positive and negative spikes kind of balance out. That it makes sense that their effects balance. And if you look at it side on, the red line is actually just the intersection of the unit cylinder with the surface. And you can see that it's flat, and that's kind of what we're saying. The whole point about this is to construct these poles and zeros such that just at this one point here on for magnitude is equal to 1, the gain is 0 dB. The gain is exactly unity. So this red intersection is flat. If I just did this for just the zeros alone, then you see the red circle is not flat. It's, the frequency response is not constant, and so the red circle is just the frequency response put on the side of the circle. But when I put the poles in there, then it flattens out. Okay, so that's the point here is we've seen that by putting these zeros at these reciprocal locations, at least for the examples we tried, we did indeed balance out the magnitude response due to the poles to get a flat gain, a uniform gain at all frequencies. But that's not quite a proof. That's more of an illustration. So, but of course we can prove it, and this is what I'm trying to do here, which is basically, well, in my geometric picture here, what I want to prove is that the length of this vector here will exactly cancel out, the length of this vector here, which is the contribution of a pole, will exactly cancel out with the length of this vector here, which is the contribution due to the zero. And basically, what we're saying is, well, we've got this all-pass filter, which is constructed as a set of terms of products of poles at some particular location, right? This is like 1 minus lambda I z to the minus 1, or if I multiply through by z, it doesn't affect the magnitude. It's z times it's this. And then we have the 0 at the conjugate reciprocal location. I'm using technically it's only the reciprocal zeros, but they always occur in conjugate pairs, so I can consider the impact of the conjugate reciprocal 0. If I multiply through by this lambda conjugate to the minus 1 z term, then this is a term whose magnitude doesn't vary with omega, right? This has just got a magnitude of whatever the magnitude of this is. And then this term, if I divide this out, then this term becomes lambda I conjugate, and this term becomes z to the minus 1. And so now the variation with z depends on the variation of these things with z. So if z is e to the j omega, the length of this term is this. It's z minus lambda I, so it's this vector here. The length of this term is lambda I conjugate minus z to the minus 1. Lambda I conjugate is down here. Z to the minus 1 plus equal to e to the j omega is e to the minus j omega. So it's this point here. So this blue term is this vector here, which is just the mirror image of this. And so we can see that the ratio of these are going to be the same length, And so their magnitudes, their magnitude ratio is always going to be 1 as we move around the unit circle. So this is to say that these two, the actual thing here is, the actual vector is this one here, right? This length here, which clearly isn't the same as this one, but it turns out that it varies the same. It's just different by a scale factor, which is the magnitude of the lambda here. And of course, you know, if you've done if you've looked at this problem before of trying to find the locus of points such that the ratio of their distance from any 2 points is constant, then that does give you a circle. I mean, it's actually it's a hyperbola or something, but in this case, it gives you a circle. I don't know. It works out. So this is just to say that, yeah, you can work through and prove algebraically that you are going to get the gain that is constant for all frequencies. Okay? Just because it bugged me that I couldn't, you know, we'd sort of just presented the answer and hadn't really shown that it works out algebraically. So this is the sketch of how to prove that. Okay, so let me just, in a couple of minutes, so any questions about this stuff? But the next thing we're going to talk about, which is maximum minimum phase, feeds onto this quite nicely. So maybe just let me introduce this and you can see what I mean. So in the all-pass filters, we had reciprocal roots. The poles, the zeros were the reciprocals of the poles. And by having both the poles and then their reciprocals as zeros, they had essentially the same effect on the magnitude. Well, the poles had divided the magnitude and the zeros multiplied the magnitude. When we combined them, they cancelled out. There's maybe a constant factor involved, but they had complementary effects on the magnitude. But they had different effects on the phase, which is why we got a flat magnitude response but a non-flat phase response. So since in our filters we're generally interested in the magnitude response, we can think about taking a particular root and replacing it with its reciprocal. And, right, so that's in terms of this rubber sheet picture, right? We've got these dips in here due to these zeros that are outside the unit circle. But if I'd actually taken, can I do this quickly? If I'd taken the reciprocals of these things, which would give me an unstable filter, but then taken the zeros that correspond to that, and then use those. So now I've got a similar looking picture, but now my zeros are inside the unit circle. But if I look at the shape of the red curve, it's still got those two dips near the zeros. And actually, the dips are the same. They look like the same shape, but one comes from being the zeros just outside the unit circle, and the other comes from the zeros being just inside the unit circle, right? And so actually they are the same shaped dips. At the point of this unit circle, these two surfaces are identical. They're intersecting because they're both being pulled down, but one's being pulled down on the outside, one's being pulled down on the inside. So we can imagine taking a system that's got a particular magnitude response and taking its roots and replacing them with their reciprocals to have the same magnitude response but a different phase response. Now, of course, that doesn't work so well for poles, because basically if we've got poles and we've got a stable system, we need the poles to be inside the unit circle. And so the reciprocal poles, which would have the same effect on the z polynomial, would correspond to unstable systems, and actually the z transform would blow up. But the zeros we can do this for. We can move zeros inside or outside the unit circle, and they're still stable, because it doesn't matter where zeros are, the system is always stable, regardless of the zeros. So we can think about moving these zeros around to give filters that have the same magnitude response but different phase response. So here's a simple system with a single real pole and a single real zero. Here's its magnitude response. It has a zero close to DC, so it has a gain that gets small at low frequencies. It has a pole somewhat close to Nyquist, so both the zero and the pole are making the magnitude response rise with frequency. Here's a different system. It's got the same pole, but now its zero is reciprocal. Instead of being at B, where B is like 0.9 here, it's at 1 over B, say 1.1. So it's outside the unit circle, not a big deal. The magnitude response is actually the same. Because of this reciprocal zero has the same impact on the magnitude response. So the magnitude response of these two systems is the same, but the phase response is very different. Here, we've got a circle around a pole and a zero. The pole gives us a total accumulated phase of minus 2 pi. The zero gives us total accumulated phase of plus 2 pi. So actually, the sort of phase goes up a little bit, then goes back down. Here, we loop around the pole, but we don't loop around the zero, so we have a accumulated phase of minus 2 pi as we get to all the way around. So these are two systems. They're different systems. They have identical magnitude response, but they have different phase response. And so and all we did was replace one of the zeros by its reciprocal. And so this is this idea of minimum, maximum mixed phase, that by taking a system with zeros and then replacing the zeros with reciprocals, we end up with systems that are equivalent in the magnitude response, have different phase response. Okay, so we'll talk more about that when we meet again next Wednesday. Any questions? All right, see you on Wednesday.